It's for me a pleasure to introduce Danielle, who is a visiting student from Lancaster University. As you may or may not know, Lancaster is a partner university for Optima. So we have this opportunity for their students to come over to Melbourne or to Monash, but also the opportunity for the PhD students from Optima to go to Lancaster. So if any of you are interested in that opportunity, talk with Charlotte. Danielle works in the STOR-i Research Center, is that correct? So that's kind of a doctoral training center at Lancaster. Am I correct?
Yes.
So her supervisors are Ahmed Kaheri and Nicolas Pavlidis. So I met Ahmed through Gecko, and that's how Danielle got the opportunity to come over here. Her project is looking into dimensionality reduction, specifically for instance space analysis. She will tell you a lot about that, and I understand that you have an industry partner, which is Tesco, which is a major retail chain. So I will let Danielle to continue with her talk, and let's take her for her presentation.
All right, great. So thanks for having me. So a bit of what I have on this first slide, Andres mentioned. So STOR-i, so that's where I'm doing my PhD, is an EPSRC Center for Doctoral Training in Stats and Operations Research at Lancaster University. It's joined between the Management Science Department and the School of Maths. And it involves, first we do a master's program where we get introduced to a wide range of topics in both stats and OR, and then we kind of start our PhD projects. And one of the major points about STOR-i is the focus on industrial partnerships. So all of us are encouraged, we either have an industry partner for our projects, or those who don't are strongly encouraged and supported in finding an internship at some point during the PhD. So my project is in partnership with Tesco, which is the largest British grocery chain, and it is a multinational company. They have over 300,000 employees and over 3,000 stores in the UK. So they have a lot of like large systems to be optimized. And in particular, my supervisors there are interested in algorithm selection for combinatorial optimization problems, with a primary interest being scheduling and routing problems. But as I started actually working on my project, we realized it's going to be a lot less application-based and more methods-based. And they've been happy to let me just dive into looking at the methods instead of being frustrated that I'm not looking at a particular application, which I think is what they initially wanted. But it's been going okay. So I'm going to talk a bit about some of the work I've been doing on dimensionality reduction for the context of algorithm selection. So quick introduction of the algorithm selection problem. So just framed as a supervised learning problem where you're able to have, for a set of instances in a particular problem domain, you're able to extract a set of features from them, as well as run a set of algorithms on them to get your performance data. Depending on what exactly you're trying to do, you decide what your class labels are in terms of best performance, and then the aim is to predict which algorithm will achieve best performance for a given problem instance. So when I started my work, obviously one of the first places that my literature review led me to was instance space analysis, which you guys work on a lot here, which among other things extends the algorithm selection framework to enable visualization. And earlier in my PhD, I did an instance space analysis on Sudoku puzzles, just to get a sense of what the methods, like how the methods actually work, and use it on a data set that had a bit of fun and a lot of stress, like creating on my own. So, but it allowed me to see what were the things that I found interesting about the actual methods. And one thing that came up were the actual dimension reduction techniques, which are used for visualizations. So in dimension reduction, the aim is to represent your data set in a lower dimensional space in a way that that lower space retains the most important properties of the original data matrix. I've been spending a lot of time, most of my time, on linear dimensional reduction methods, where you can express your projection matrix in terms of the product of a transformation matrix and your feature matrix. And the most common basic dimension reduction method is PCA, which aims to find a projection that retains the maximum variance of the data subject to like orthogonality and things like that. But the issue, of course, is that the directions of maximum variance in F may not necessarily be useful to explain the variability in Y. So that's when we start looking at supervised dimension reduction methods, which actually take into account the performance space while you seek to project to a lower space. So as I've been looking at these methods, the kind of question that we've been asking is, how are these methods different? Not necessarily trying to find best for, say, this is the approach we need to be using whenever we're doing any analysis like this, more seeing what the interesting differences are depending on what the method is, and possibly seeing what cases certain methods might be more appropriate, but it's really more just comparative and investigative at this point. So I'll talk about a few approaches. So the first that I'll talk about is pilot, which is used in the instance-based analysis framework, which aims to find a projection that simultaneously captures linear relationships between the features, as well as the performance of each of the algorithms that are being considered. There's the analytic solution, which is pretty straightforward to calculate and is quite similar to PCA, just that it also includes the performance in the calculation. And then there's the numeric solution, which is very often quite different from the analytic solution. And that's something that I'll mention when I start looking at some results. Then since I've been here for this visit, there's an autoencoder for instance-based analysis that one of Andres's students, Anthony, has been working with. So I've looked at that as well, which is basically trying to minimize the same objective function, but instead of using more direct numeric approach or just transformation matrices, using actual autoencoders to do that. And depending on the settings of the model, so the number of layers or the type of activation functions, you're able to get either linear or non-linear projections. So there are also more traditional statistical / machine learning approaches for supervised dimensionality reduction. So I looked at two of them. The first one is linear discriminant analysis, which aims to maximize the separability among the known classes in the data. So it's the optimal projection maximizes the variance of the across class means and minimizes the variance, the within class variance. So basically, it's trying to create a projection where if points are in the same class, they're as close together as possible, but those clusters of different classes are as far away from each other as possible within the data. And there's a pretty neat form to that solution, which is composed of the eigenvectors of those scatter matrices, the within class and between class scatter matrices. The biggest limitation of linear discriminant analysis is that it's a very strong reduction method, in the sense that if you have K classes in your data, you will have at most the K-1 components. So if you're only comparing two algorithms, you get just a line, which isn't necessarily the most interesting for visualization. The other method that I've been looking at is partial least squares, and that aims to find a pair of direction, and that's a recursive approach, and it aims to find pairs of directions that project your feature matrix and your performance matrix in a way that maximizes the covariance between those two projected vectors. After you find that projection, you deflate your pre-trend performance matrix, and then you keep repeating that until either you have the number of components or that you'd like to work with, or until you cannot deflate the matrices anymore. There are a few ways that have been using this. So the first is the more standard way, PLS regression, which just uses your normal performance matrix, and this is directly related to the performance prediction problem. There have also been considering using the relative performance. So given the performance matrix, you consider what is the performance of a particular algorithm relative to the best algorithm for that particular instance. And that is more directly related to performance comparison. And then there is also PLS discriminant analysis, which is very popular in chemometrics, which you give it the dummy encoding of your class labels, and that's directly related to the algorithm selection problem. So I'm going to talk about like some of these. I'm going to talk about these on a more visual level now, but since I'm more focused on methods, there's no point just showing you pictures for different data sets without the wider context. So I'm more going to be talking about different ways that have been like evaluating the projections, and then the other pretty pictures. Are there more for reference or to support a point, since the picture doesn't really mean anything if you don't know what the problem is. So when looking at dimension reduction methods, there are several metrics in the literature that people have been using to kind of evaluate how good methods are. So one of them is shepherd goodness, so a shepherd scatter plot is just a plot of the distance matrices of the high dimensional space versus your projected space. And if you do the Spearman correlation of that scatter plot, then you have the shepherd goodness. And this is kind of giving you a sense of the level of preservation of information as you move down from the HD space to, in this case, the two-dimensional space. The main thing of note looking at these metrics is that, for one, principal component analysis and the analytic solution of Pilot generally retains the most information, and not just for this handful of data sets I've shown here, also for several others that I've looked at. And that kind of, so there's that, but also of note is that linear discriminant analysis doesn't preserve a lot of information, and I'll get into a few more details about that shortly. Then when you look at all the other methods, it's a more case-by-case thing. But very similar to shepherd goodness is the normalized stress, and this almost shows you the same thing, but just in reverse, where you want the normalized stress to be minimized, but it measures like the preservation of the pointwise distances. So whereas before you were looking at the correlation between the distances, this is more looking at just the differences between the distances. So the thing of note here is that whereas before it was clear that PCA and analytic pilot were the best, and they're still the best in this case across all of these data sets, and you saw that LDA preserved the information the worst. When you look at it from this perspective, you also see that the linear autoencoder, so that's the red lines, as well as the numeric solution to Pilot, you see that those also don't preserve as much information as it appeared that they would have when you look at the normalized stress, not when you look at the shepherd's goodness. But the thing is that we're not necessarily interested in preserving all this information when you move from the highest to lowest, highest to lower dimension, because if you have a lot of features and you kind of just throw it into your model, then not all of it will be useful. So if you're not preserving that not so useful information, that's kind of a good thing. So whereas these metrics might be good for measuring the quality of dimensionality reduction methods in some contexts. In this context, they might not necessarily be the most appropriate. While they do give some information, it's like, okay, it preserves the information, but we kind of want a bit, we want to achieve other things than just preserving information. So there are two main ways I've been looking at that. One of them is kind of our ratio of the correlation. So it's similar to the Shepherd's goodness, but now we're looking at the correlation between the high dimensional matrix, so your feature matrix, to the algorithm performance matrix, so the correlation of that, versus the correlation between the lower space, so your Z matrix, to the performance matrix. So if that ratio is about 1, then you're kind of getting the same amount of information about the relationship between your projection and the algorithm performance, which is what we're interested in. If it's less than 1, then you're losing information by going to a lower dimension, which in some cases is a reasonable thing, but it's also possible for you to gain a lot of information, which happens when that ratio is greater than 1. So I'll talk about this plot a bit. So as you saw for the TSP data set, you'll see that most of them are at just either slightly above or slightly below 1. And part of the reason for that could be, again, this is not like proven or anything, more just observation and like inference. One thing about that TSP data set is that it consists of a small set of well-constructed features. So the features are already giving you a lot of information. So there's only so much that can be gained from reducing the space, considering the actual performance matrix while you're reducing its kind of thing. Whereas, for example, this VRP data set, which has over 100 features and can just throw all the data into the model. So it's like, okay, here's all this data, see what we can do. There's a lot to be gained by reducing the space in an intelligent way, because might be redundant features, there might be features that actually just aren't related to the performance at all. And all of that would kind of get sifted out as you do the dimension reduction. And then some methods do that sifting out better than others. Most notably is the linear autoencoder and the 3 lines in the middle, the autoencoders, as well as the partial least squares. So yeah. And then the last thing that I've been using to kind of evaluate these projections is the neighborhood height. So that's the average proportion of for each of these points in your projection, if you take a point and you look at the k nearest neighbors, how many of those nearest neighbors have the same class, and you're averaging that across all of the points. So we're interested in seeing, one, what the class structure looks like in the visualizations, as well as how large those clusters are. So one thing that becomes evident is that linear discriminant analysis. So that's the green line up here, middle green line here, top green line, and then it's kind of blended in for this first one with the purple line. That consistently does well in showing the separability of the classes, because LDA is both a classification model and a linear and a dimensionality reduction method at the same time. So it inherently tries to separate the classes, and it maintains kind of a flatter line than a lot of the other methods, because there are larger clusters that you're able to see in your structures. And the other thing I'll point out is that, okay, I guess I'll just go through some of the comments, and if there are any questions, I can always go back to some of the plots for more specifics. So there's the similarities between PC and the analytic pilot, which I mentioned would be because of just the form of the solutions being very similar, particularly if you have a lot of features then when you add two columns for performance, they will get dominated by a lot of features. So then you'll end up with a very similar projection as PCA. And that's kind of reflected in a lot of the figures I showed you, where the bars are about the same, or the lines kind of follow the same pattern, where one might be slightly better than the other, depending on exactly what you're looking at. So those two are very similar. And then there is that the numeric pilot and the linear autoencoder also are very similar. And that's with a very strong caveat that it assumes that the numeric pilot has actually converged. And so there's an issue with that. And since that's something I've more recently started looking at, don't have a good solution / answer to this, but depending on how many features were just the original dimensionality of your data set, the numeric method might need several runs to find a good solution, unless you actually kind of just trim down your set of features before. So it's really a matter of how you decide to approach with that. Another thing that I've noticed is that the success of the partial least squares methods varies depending on the distribution of your performance matrix. So I've not shown specific results for that in terms of the distribution. But one thing I've seen is that if your Y matrix has a very large spread, so for example, there was a TSP data set, so not the Matilda TSP data set, but another traveling salesman data set that I've been looking at, where the problems are of very different sizes. So there are some small problems, so the solution, the performance will be like 1,000 or hundreds. And in that same data set, there are very large instances, so the performance will be like in the 50,000s, things like that. So because of the large spread of that performance matrix, the partial least squares models kind of struggle. Whereas if there's more a smaller range, not as great degree of variation within the distribution of the performance. So with some other data sets, it is a lot better able to separate the classes and just extract more useful information in the projections. And the last thing of note in this part is that, and I'd mentioned it, is that the LDA, you're able to see larger clusters of the same classes because, as I've mentioned, it's inherently trying to separate the classes, so you're able to kind of see things more clearly in that regard. So another thing that I've looked at with the dimensionality reduction methods is using them for actual prediction. So instead of we get the Z matrix and use it for the visualization, and then you do the prediction separately, actually incorporating that reduced space into your prediction model. So that is something I've looked at and will probably extend a bit after I go back to Lancaster. So when I've done this, we're using just multinomial logistic regression models kind of as a baseline classifier, and considering how do these different projection methods work when we throw those Z matrices into your classifier. So this is the same VRP data set that I had mentioned a few slides earlier. And you see that there is generally pretty good like class distinction between the orange and the blue points, also, and that's the predictions. But of course, that really doesn't mean anything if the predictions are wrong. So we are able to also look at the different classification evaluation metrics, and we found that using so this is for this particular data set, we found that using the relative partial least squares model did a lot better than some of the other models. And again, I'd mentioned it depends on from data set to data set, whereas the distribution of the Y matrix here was pretty I won't say normal because it wasn't normal, but it wasn't like, oh wow, why does that look like that? It was a more consistent pattern in the spread of the data sets, in spread of the performances, sorry. So some general comments about that work that I had done. So I looked at about four or five data sets with that. If the first thing is that PCA required considerably more components to get as good quality predictions as the supervised methods. When I was doing this work, I was only looking at the analytical version of Pilot, and that required more methods as well than the other supervised methods, while having very similar performance to PC and the reasons I've mentioned before. Also, LDA was just as good as classifier for classification. And as I mentioned, it showed the best separability of the classes. And then the discriminant analysis version of PLS and the relative version of PLS were also better for classification than just the straight traditional version of partial least squares. So in terms of kind of further work, and I plan to mostly do both while I'm still here in Melbourne, and then when I go back to Lancaster to finish my PhD. So the first thing is actually considering footprints. So to see how do the footprints like look different in the different using the different projections, and seeing if the metrics for evaluating the footprints actually change just because the actual original space is a bit different. Also interested in looking at this, but in 3 dimensions. Again, one of Andres's other students has been working on the 3-dimensional space. So I'm interested in doing a bit with that. And then more longer term, when I get back to Lancaster, there are some other methods that I'm interested in looking at, particularly those that kind of do both classification and dimension reduction together. So LDA was one of them, but LDA has a lot of limitations, but there are some extensions of LDA that kind of overcome those limitations. So I'm interested in looking at that. And a few other things that kind of involve using more of the data in a way that allows for classification and dimension reduction together.